So we're going to look at how we simulate some spatial model specifications. This notebook goes through a whole range of them. I'm just going to focus on the spatial lag model. You'll see the mechanics are always the same. And this time we don't read a data set because we're going to make our own data. But we still need, in fact, we need more modules and some different modules. So NumPy, Pandas is to work with the data. Time is optional. That's to time how long the experiment runs. Most of these are a few minutes, but it depends on your machine. And for example, my other machine runs this 10 times faster than this little laptop. So it does matter for some of them. For others, it's between, you know, half a minute. That's not going to make any difference. Again, if you want to make graphs, you need matplotlib. I talked a little bit about the logic of matplotlib when we talked about making maps. Seaborn is actually on top of matplotlib. It's a little, for some things I prefer it, for other things I'd rather use the original plot functions. And then we have from spreg a whole bunch of things. Okay, OLS, because we're going to estimate the model as if it was a classically squares model. And then these are all the data generating pieces. Make X, make XB, make WX, make WXG, make error, DGP lag, DGP error, DGPS-LX, DGP spatial Durbin, and there's others as well. So you can, the logic is the same always. You set up the design, you generate the error terms, then you combine the error terms with the X beta or X beta and WG, XG in a spatial Durbin to use the data generating process, say spatial lag, to create a vector of Y variables. Then you regress these Y variables on the X, no spatial model. You get the beta. You put the beta in a big matrix. You plot the distribution of the beta. You get the descriptive characteristics of the beta and so on. Now, these models are all very simple. They only use one beta, but you can use two betas. You could put in multicollinearity. You can put in heteroscedasticity, non-normality, all kinds of stuff, and look at the effect of that. Okay, so we have all these different functions. We set up the model. Let me make this a little bit bigger. So we're going to do this for a regular grid. You don't have to. That is something, if you wanted to try this out, say, what would this look like for US counties? Or we have a data set where we have Brazilian municipios. There's a little over 5,000 of them. So you can check this for different size data sets. Here I use a square grid, and grid X is the number of cells in the horizontal dimension. Grid Y is the number of cells in the vertical dimension. So you can make them square or rectangular, but they're grids. Then B1 is a set of coefficients. And this gets a little complicated, so you have to really pay attention. B1 includes the constant term. So in this case, we have 1 for the constant term, 1 for the beta coefficient. You read a random seed. If you don't set the random seed, then every time you do this, you get a different result. Random number generators are mechanical. They're actually deterministic. They start from something and then they build a series. You set the seed to start from the same point. If you don't do this, you don't have reproducibility. So it's very important. Number of replications, I kept it at 1,000. Then we have all the parameters. So the values of rho, that's the autoregressive coefficient in the lag model. That's the only one we're going to look at today. Values for lambda, values for gamma, and so on. So this is all set up here at the top. Did I? No, I didn't. So I do all my modules, and then I set the parameters. Then one more thing, we'll need spatial weights. These are constructed using the function lat2w, which we saw in the notebook that dealt with spatial weights. And we make them queen, we set rook to false, and re-row standardize them. So here we have our weights for the regular grid. So now we have to make all the pieces, and there's some pieces that we only have to make once, and there's some pieces that we have to make for every replication. So the things that don't change are x. I mean, you could make it change, but we keep it fixed. And x beta, we keep that fixed. Remember, the regression specification in classic OLS is y equal x beta plus the error term. The error term will change each time. X beta doesn't change. Y changes each time. Right? If we do the spatial lag, we get it from the reduced form. Y is I minus rho W inverse times X beta plus I minus rho W inverse times the error term. So we create the error term, we have X beta, we do this inverse stuff, we get Y, then we regress Y on X. We get a beta, we stick it in a matrix. Okay, so the X, this is more general, this does the cases for spatial Durbin as well. We don't need that here. So the X is doesn't have the constant. Remember in spreg, you do not pass a constant, but XB needs a constant. Now the make XB takes care of that. Okay. So at the end of this, we have X1, which we'll need for the regression, and XB1, which we need to make the Y. Okay. Then this explains how we do the spatial lag model. So this is what we're going to do. We initialize a result matrix to hold all the betas, 1,000 of them. At each step, 1,000 times, we're going to generate an error term, generate the Y using the DGP that we want, in this case, spatial lag, and then regress Y on X and get the beta, pull out the beta. Then we do this over all the possible combinations. Say we look at all the different values for rho and take the matrix, it's an array, return it into a data frame, then we can do descriptive statistics, and we can use plot functions and all that kind of stuff. Okay, so let's see. First, we initialize. This is where the NumPy stuff comes in. Typically, there's not a lot of programming involved in what I cover, but this is a little bit more. It's not rocket science. It's once you get the logic, it's really easy to do. And in fact, you don't have to do anything. You could just use it as is, change the parameters and the sample sizes, things like that. So this is a matrix of zeros. It's not always the best way to do it, but oftentimes, if you know ahead of time the size of your result matrix, it's more efficient computer-wise to reserve that memory space ahead of time, rather than, say, build the matrix one row at a time by appending a row each time on the matrix, because that requires that the program refigures out where all this stuff is, whereas here you have it set up ahead of time, so it's very efficient to store the results. There's just something to keep in mind. Then here's the simulation loop. So we, as I said, I use the time function. This is handy, for example, if you do some programming to figure out if changes that you make the program more efficient. You just time it. You initialize the random number. This is just some gobbledygook that comes straight out of NumPy. So you have to set a random default. A random is a subset in NumPy. It all changed recently, but this is, without explaining it, this is the way to do it. So this sets the seed, and then we're going to do this for values of row that are contained in the row value list, right? And for I is just a counter. This means we're going to do this 1,000 times, right? First, we make the error. Make error is in the DGP module, and we do it with a random number, and we make it having n observations, which is a vector of, in this case, 400 error terms, independent, almost stochastic, right? Then we use this DGP lag to take the error. The error is different for each simulation. XB1 is the same, W is the same, and we pick the value that we need for row. This makes the Y, and now we do the regression of Y on X1. And we keep it simple. We pull out, remember I said all the results are given to you in a summary. There's no point in printing 1,000 summaries. You just pull out the beta that you want, and then we're set. So I can't remember how long that takes, but it's not very long. I think it's like a minute or so at most. So we let this run. While this runs, I'll tell you what goes on here. So then we just do some funny business. So in order to put this into a data frame, you need to give columns to the data frame. So to remember what values of row you used, the first time it always takes a little longer. Oh, here we go. Okay, so less than a minute, right? So now we have our full array of our 1,000 estimates, and we're going to turn this into a data frame with a columns set to the elements of this. This is a little bit of Python stuff where it's called list comprehension. If you've never seen this before, it looks kind of weird, but it's kind of like a loop inside a list. So we're making a word, row, plus the string value of the coefficient row, and do this for every value in our list of coefficients. That gives us the column names for our data frame. So then if we look at the data frame, there it goes, row 0, row 2, row 3, okay? You may do it differently. There's multiple ways to do this. Then we can look at the descriptive statistics. And here, two things to look at, and I talked about this in class. We have the mean. So the true value is 1. We are just about at 1 for the null case. If we increase the number of replications, we talked about that the other day, it will get closer and closer to 1. But as we move away from 1, it becomes more and more different. So by the time we're at row 0.9, is basically 1.4 on average. And the other thing to look at is the standard error, which we see doesn't change much in the beginning, but then it starts doubling and even quadrupling. So those are the two effects that we saw in the lecture notes. Now we can plot each individually. This is actually not that interesting, but here's a plot for row equal 0.5. You can make this fancier if you want to, but what I like is to put them all together. And there's actually simpler ways to do this, but I just use this one where I use this particular function melt. This is a pivoting operation. So you have in R, you have tidy data, where you have the wide form and the long form. So it basically turns a table from the wide form into a long form. So the wide form is for every value of row, we have a column. The long form is we stack these on top of each other. And then it's easier to make a graph for all the different values. You see how this is stacked on top of each other. And then if we do the plot in Seaborn, we use this plot and we change the hue by the value of row. So the variable that we plot is the beta, and this gives us this very same plot that we saw in class. Okay, so the principle is the same. I have this as examples for spatial error, autoregressive error, moving average error, SLX, spatial Durbin. You can do any number of different ones using this same template.